Now with our lemma 5, we'll be able to simplify this summation a little bit. We'll be able to grade this by the rank of y. Specifically, we have q raised to the power n minus 1 times the number of nilpotent matrices which is the summation of m of y over all non-zero or admissible matrices will be equal to the summation of m of r times the number of rank r or admissible matrices from r equal to 1 to n. Because we removed the zero matrix, all the rest of the matrices will be of the rank at least 1. So, to study the number of nilpotent matrices, it suffices to compute the number of rank 2 admissible matrices as well as m of r. This guy is easier to compute, which will be addressed in our lemma 6. Which states that the cardinality of AR will be equal to q raised to the power n minus 1 times q raised to the power n minus q times the all the way to q raised to the power n minus q raised to the power r minus 1, which is the last term. So let's prove this. For any y in A sub r, where r is equal to 1, by lemma 2, we know that if y is written as the block matrix consistent with row vector as blocks, then y1 through yr are linearly independent over fq, and the last n minus 1 rows, namely y sub r plus 1 through y sub n, are equal to 0. And now we will look at the choices for y1 through yr individually. Let's first look at the choices for y1. How many choices do we have for y1? The first row, y sub 1, can be anything except for 0. So there are q raised to the power n minus 1 choices for y1. And y2 can be anything except for the fq span of y1. So there are how many? Should be q raised to the power n minus q choices for y sub 2. And you continue with this procedure. In the end, y sub r can be anything except for fq span of y1 through y sub r minus 1. So there are q raised to the power n minus q times, so there will be r minus 1 q's, corresponding to all possible choices for the coefficients of y1 through y r minus 1, which is q raised to the power n minus q raised to the power r minus 1 choices for y sub r. And if you multiply those r things together, it will give you this product as the number of admissible matrices with rank r. And that is the end of the proof for lemma 6.